All right, awesome. We'll get going. It won't fill up the whole hour unless there's discussion, which I would welcome especially for this talk. Like want to welcome discussion because so I've given like, I don't know, 5 of these talks, the future of fMRI, and sometimes, it's hard. It's a really hard talk to sort of give because I mean you could give it in an easy way if you just simply say, oh well, things will, get high resolution somehow and they'll go faster and they'll make new discoveries and maybe it will be clinical and that's it. So yeah, and so for this talk, there's a little bit of that, but what I wanted to do for this talk though is kind of have a realistic view of kind of what has happened and get a sense of the big things that have been going on in fMRI in the past 30 plus years, and then sort of try to interpolate a little bit, but then interpolate kind of in a realistic way. But so I don't go that far out. But anyway, I every year, every time I do this, I do my best in trying to speculate. And also this sort of naturally flows from the previous talks I gave on challenges, because a lot of the future is involving overcoming the challenges. But this is a little bit more of whether we can overcome the challenges or not. And also the mysteries and sort of the prospects and things like that. So, all right. So what have been the big advances in fMRI methods? Not necessarily all the discoveries, because there's been, 80,000 papers. And this is more just sort of like my sense of the methods. And I'm sure I've missed a few things, but and certainly there's been hundreds and hundreds of little methods that have developed, but this is sort of like a sense of like how the methods have improved. So I put resting state at the top because I actually think this is the biggest discovery in methods in fMRI ever. 1995, it was discovered, and then it sort of caught on around 2006. And the reason why I say that is because it's something truly unique to fMRI, and it completely. Well, we might want to shut the door. Yeah, it completely kind of created a new paradigm. EEG never really looked at resting state that much, maybe a little bit, but PET certainly, they would look at metabolic state, but not look at, connectivity. So resting state connectivity was something brand new. That's sort of a paradigm shifter. So that was the biggest thing. Other big advances, and this is sort of a cumulative thing, but it's for the most part been all good. People say fMRI is an indirect measure of neural activity, but it's been pretty well validated, not only from behavioral measures and not only from, Logothetis's papers with single unit electrodes, but from other methods, calcium channel imaging. And there's been some discrepancies that are kind of interesting, but for the most part, it seems that for what we care about, if there's an increase in activation, it goes up, a decrease, it goes down. Whether it's inhibitory or excitatory, that's a mystery that we'll probably figure out. I think we're relatively close to figuring that out. Another big advance in methods has been just standardizing or having these big platforms that help everyone sort of get on the same page in terms of analysis. Sort of a cultural thing that's a big method advancement has been the growth of shared data sets and code. These amazing data sets. Human Connectome Project has been unbelievably useful, and other ones are variously useful. Yeah, this is probably the accumulation of all these brand new clever paradigms that have been sort of trying to tune to the fMRI signal, but also to use behavior in a clever way to pull out more information. That's sort of grown. Didn't really have a chance to exist that much in other imaging techniques, maybe EEG a little bit with ERPs, but otherwise, no. And in fMRI, aside from resting state connectivity, I like to think that voxel-wise pattern assessment, the idea that instead of looking at blobs, fMRI had a really bad reputation up until multivariate pattern-wise voxel assessment kind of came on the scene, because before it was like, oh, you look at a bunch of blobs and what blobs are active. Here now we're looking at voxels and seeing the patterns and saying, okay, there's information within that blob that we're able to pull out by looking at the pattern of the blob, within the blob. So that, I think, was a major advance. In terms of pure acquisition, we don't even notice it, but sense, parallel imaging techniques, sense, grappa, other multi-band acquisition that uses the coils to speed up the acquisition was huge, was really, really important for a lot of our high resolution work, and also whole brain work. So for whole brain, we wouldn't be able to do whole brain in the TRs that we use unless we had these. So these were breakthrough advancements. High field is the next big advancement that will open up for even higher resolution. Obviously with high field, vaso, multi-echo. Multi-echo has been around for years, but is finally catching on, especially in the context of individual subject assessment and wanting to get a lot of signal to noise in one time series. It seems like it's kind of like above that threshold of, oh, you actually absolutely need that to do this well. So that's important. And of course, sub-millimeter spatial resolution, it's caught on less than I sort of expected at this time, since it's been around for several years now, but also because it's so hard to do. That not only will it give you more detail, but of course, with layers, it might give you brand new information. And this has been important. This is kind of to me, the most boring sort of thing, but it's one of the more important ones, that efforts to make the data more reproducible, all the data more replicable, through Russ Poldrak's sort of heroic efforts with OpenNeuro and many other people that were involved in that. So that's sort of a cultural shift that's being propagated by these websites and tools. And we're all kind of aware of that sort of thing, because I think for a while the field went through some sort of a dark ages of, up until 2010, of like, hey, we have our database, we have our 20 subjects, one disorder, 20 subjects of healthy controls, we see a difference, we look at our blobs and we see a difference, and there you go, and then it's published, and almost useless. And that was going nowhere. So that really helped as far as that's concerned, actually making us all aware of that problem. Dense sampling. This hasn't yet happened, but I think this is our next big advance. I mean, it sort of has happened, because people have been doing dense sampling since even before Javier did his 100 runs on one subject. And individual assessment, subject assessment, which is the idea that, and also people have been sort of doing this with retinotopy since the beginning. Vision neuroscientists who came from the culture of looking at one monkey and looking at FDG or something like that, and writing a science paper based on one or two monkeys. Now, if we're really densely sampling an individual and we're not trying to draw inferences about differences in populations, then we can say, hey, there's a lot of high quality information that you can get from this directly registered data set, where you don't have to worry about anything other than how they may change over time, and you're trying to keep that constant. So I think that a lot will come from that trend. All right, smaller advances, I'll go over this quickly. Quality has gone up. I mean, it's sort of like general trend of things have gotten better. Temporal stability, sensitivity, resolution, and speed. Standardization of acquisition, processing, display. So explosion of methods, processing methods. These are all things that have gotten better over the years. Artifacts, and a lot of these things are kind of in our blind spot. I mean, artifacts are better understood and they're both more fully removed, in part because what's been going on in the community, but also in part just because the vendors have gotten better as far as addressing this as well. spatial resolution that most people use has gotten better. For about 15 years, it was 3.5 millimeters. And then finally now it's about down to 2 millimeters, which is good. It's not as high as it could be, but it's good for most people. Multimodal integration is more common, even though, like I said, right from the very beginning, a lot of people maybe were doing it, or some people were doing it, but now it's becoming more of a thing. Like, oh, simultaneous EEG and fMRI is more catching on. And other integration, like integration with diffusion imaging or other modalities. 3T is standard. It became standard, in the early 2000s, but that's a small advance. Real-time neurofeedback. I actually think of this as a small advance because it's not just sort of a thing you do that you show a demonstration of the scanner, like, oh, wow, look, the real-time activation. I think that there's the papers that I've seen, and there's been a lot, and there's been whole books written on this now. I think it has potential for clinical application. So I think that advancement of real-time feedback is more useful than I think we'll realize. And then clinical, the small advances, pre-surgical mapping is a small sliver of clinical applications, has a potential for neuromodulation guidance. Okay, what's been the true impact of fMRI? So I think that, and I'm not going to list the actual discoveries of fMRI that are unique to other modalities, but I will just talk about sort of, and fMRI connectivity especially, like connectivity analysis I think has catalyzed the whole idea of looking at connectivity over time and resting state and with tasks, and the idea of networks has kind of reshaped how we think of human brain organization. Before it was all like areas. Oh, what does that area do? What does this area do? And now it's more a question of connectivity. That's been, I think, a real impact of the fact that we have so much flexibility of looking at the whole brain over time. I think fMRI lends itself most, and these are things that are hard to do, at least to map, like with PET and any other mapping techniques, is looking at changes with learning or adaptation or plasticity. That's been a real impact. And this is sort of linked to the first one, the idea that we're looking at the brain from a network perspective, and how do the networks relate to tasks and states and traits and also spontaneous activity. So that's something that we don't really think about, but I think that without fMRI having come along, we wouldn't even, it would be way more abstracted than it is now. When we think of networks, we think of, oh, there's like, anywhere from 50 to 120 networks that we understand in the brain. And that's thanks to fMRI. No other technique can do that or even come close. I think it recatalyzed. I mean, there's been the scientists plugging away, looking at neurovascular coupling for years, and especially in neurology, they care about this in terms of stroke, but never to the degree that people care about it when trying to interpret fMRI data. There have been some really, really outstanding pieces of work trying to understand and really dig into neurovascular coupling and brain metabolism that have shed light on, what causes neurovascular coupling and why does coupling occur? And what is the energetics? What's the change in metabolic rate with the brain with activation or at rest? So all of that has been tremendously catalyzed by fMRI. Wouldn't have happened otherwise, I don't think. And I think recently, I think that, and especially we're right at the beginning of a huge shift and people are already seeing it, that instead of, I think that the Merrick paper was a major paper because it kind of, was a line in the sand, basically saying, hey, you can't do group comparisons unless you know exactly what you're doing. And if you just try to do a standard group comparison between one population and another, you need 2,000 subjects. And I think the important message from that paper was that is not that fMRI is not sensitive, uh, as that could be. It could have been because fMRI is not sensitive that you need 2,000 subjects. It's because there's so much variability between subjects that we're not accounting for. So variability in the anatomy. So how do we spatially normalize things? I think what has been helpful for time series analysis and multi-subject comparison has been the whole process of parcellating the brain. But I think now we're going to have to take some steps backwards. It's because the standard parcellation paradigm, like where you parcellate the brain into, let's see, various atlases, I think that's a dead end, honestly, unless we figure out way better ways of parcellating in an adaptive manner. Because even a paper that came out recently on single subject, looking at with multi-echo, saying, oh, depressed patients have certain parcels that are much bigger than regular subjects. So if you put them into a standard parcellation atlas, you're going to just completely mess that up in terms of comparison. So I think that as amazing as that work has been, unless we can find better ways of adapting the parcellation to each subject and even adapting it over time, that's kind of a dead end in terms of looking at things. And so that Merrick paper sort of pointed to all, and not only that, there's differences that we're beginning to realize. You can't just say, oh, these patients have psychosis, because there's so many subtle differences between the different types of psychosis diagnoses. And even among the people who have the same diagnosis, there's subtle differences in brain structure and dynamic function. So I think that what fMRI has done, it's really made us realize that subjects, healthy individuals, individuals with pathology are all similar and different in many, many ways that we're just barely getting a sense of. And there'll be a whole science. I think there'll be a whole subfield of understanding similarities and differences. And I think this might ultimately lead to, and this has been pushed by the NIH, there's the RDoc initiative, in which they're trying to tie brain imaging features to behavior to help make diagnoses. And we're realizing, oh, we can't use the diagnoses as a gold standard because that's kind of arbitrarily mapped to how the brain is organized. So we're gonna have to figure out how the brain changes and then use that to reshape our diagnoses. So the DSM-5, the psychiatric diagnoses might have to be completely reshaped eventually by brain imaging. It's nowhere near there yet. And I don't think we're anywhere close to finding any biomarkers for any sort of pathology. I think that's kind of, for the next several years, is kind of a dead end until we have better methods. But I think that fMRI's real impact is starting to show in this area that it really has opened up our eyes to how individuals are similar and different in many, many different ways. Okay, so fMRI has had hardly any clinical impact, none. Pre-surgical mapping is sort of a niche thing that's sort of helpful. Surgeons usually prefer putting their grids over their brains and going with that. So it's a little bit less invasive, but it hasn't quite caught on. And I'm sort of going out on a limb because I think it has brought some insight into not really insight, but information about how the brain is organized. We know a lot more stuff. We know where certain sub areas of the prefrontal cortex are. We know how certain parts are activated for specific tasks. We know, all the networks. Do we have real insight into principles of brain organization or brain mechanisms? I would say no. And I think that we will get there, but I think you'll need more help from more than just fMRI. And I'll talk a little bit more about that later. Not going to go into too much detail. I'm just clumping these into three categories. One, possible future impact of fMRI. So I think I just listed the top 4 clinical applications off the top of my head. So the kind of low-hanging fruit is guidance for neuromodulation. Because everyone's different, put a person in a scanner, you do a task, you find out the part of the brain that's unique to the pathology, that's unique to the subject, and you use TMS to try to either excite it or suppress it. That's pretty, and also we're getting better at modulating the brain, not only TMS, but focused ultrasound, which I would never volunteer for, or infrared laser. I don't think I'd even volunteer for TMS, to be honest, but that's just me. And infrared laser, which is kind of bizarre, but people find that if you have infrared lasers, that activates the mitochondria a little bit more and activates things. It's worth maybe even trying an experiment. It's very non-invasive. Assessment of the individual changes over time. I mean, as illustrated by the paper I showed by the WashU group, Nico Dozenbach, in which a subject had a cast on their arm, and they showed that between left and right motor cortex, there was this, within hours, a drop in connectivity. And then after 2 weeks, they took the cast off. Within 2 hours, there was an increase in connectivity. So that just shows that that resting state is really sensitive. And I think it's sensitive to, we don't know what it's sensitive really to, but I think it's to prior use during the day, in the previous hours of whatever your brain was doing. It's sort of echoing that for whatever reason. So that could be a very interesting thing for looking at changes over time with recovery or therapy. And actually, just once again, the paper that I referred to, I think it was by the WashU group, looking at depression. So actually here they were actually looking at individual subjects and following them over the course of, I think, a year as their depression waxed and waned. And they found very specific network changes with their depression as it waxed and waned over time. So that's individual subjects looking over time. That's a clinical use, clearly. Neurofeedback with therapy. I actually think, I'm kind of going out on a limb here. I do think that there's some potential for using fMRI for especially with PTSD or something like that, using it for neurofeedback. And it might even, change some sort of psychiatric traits as well. And then the fourth one is less neuro and more neurovascular. I think the real low-hanging fruit is there's tons of information about your neurovascular health from the fMRI data. Just looking at the pressure wave, the work by either the MGH group or the other groups in San Francisco and whatever, like Blaise Frederick, for instance. Just looking at the pressure wave from the cardiac EKG signal to the brain, you look at the latency of the pressure wave, you get a sense of vascularity. You look at the pulsatility of the flow. If it's too pulsatile, too far down the vascular tree, that's suggestive of some hardening of the vascular system. So where it's not dampening the pressure wave. So that there's all kinds of potential information that could be had there. That people have shown. It's just a matter of using clinically. That you can't get otherwise. You can't otherwise get this information inside the brain. So I actually think that in terms of clinical applications, I don't think the big scanner vendors will really drive it. I think they're very conservative. They're waiting for a clinical market to open up, and then they'll jump in. What's going to open up the market is, third-party vendors, some startup groups that sort of want to do fMRI at a very low scale. They'll get something working, and it'll slowly grow from that. And I honestly think that it might happen sooner, but I think 20 years is a good estimate of when every scanner will have, like, an fMRI option that like, oh, this is what we do fMRI for, and all the clinicians will know it. 20 years. I actually think right now, honestly, I think 70 is at risk of and I might be overly conservative because, but it's super expensive. It's been around for 15 years, and um, it's there's only 120 scanners. That's a lot, but relative to 40,000 or 20,000 3 Tesla scanners, it's nothing. And so I don't, the big vendors, you need a big vendor to make it, and the market's not very good. It's just research. We haven't found any killer apps for 7 Tesla yet clinically. So if that doesn't happen soon enough, sooner, it could be a problem. It could be a problem. Or it could just keep on living like a classic model of having a Ford having like a Formula One, sort of program that they just kind of keep it going. And obviously the market, we don't make a lot of money with that much money with 7 Teslas. So I don't know. I think, and it could be something for pushing the technology, but it's not yet hospitals are not buying 7 Teslas. So I think resting state still has a story to tell. And what I mean by that is we don't really understand resting state. We don't know why it's there. We don't know what its evolutionary purpose is. We know it indicates a lot of things. So I think that there'll be more discovered with it. But I also think that, like, for instance, in the context of the cast and everything, I think that there might even be ways of augmenting using TMS or whatever, resting state connectivity, that could be an interventional therapy. Now I'm just kind of going out on a limb completely. So there also might be surprises in, our vast pulse sequence parameter space. So, right now, physicists love to play with sequences, and there's about, 20 different things you can do with a sequence. And we haven't really explored that space completely with what we can do with RF, what we can do with the gradients, and what we can do with the timing. And so there might be some surprises there too. I think there's more possible contrasts from not only one image, but like, the combination of synthetic images, along the lines of fingerprinting, where you try to embed as much contrast as possible in one time series. Here, there might be a way of like getting 5 different contrasts, and then from the interaction of those, there's something unique, some multivariate contrast assessment. So it's very easy to say AI is going to change everything, and I don't really think it will. I think the big problem with AI with fMRI is that AI is right now still, the algorithms for AI are kind of too stupid to learn, in the sense where, it needs, with YouTube videos, it needs millions of training sets, and there's just not enough training sets with fMRI to train AI, really well. AI will get better, and obviously processing is the biggest future thing in fMRI. I think one of the biggest things. Processing methods keep on evolving, and the more people look at big data, the more they're processing and coming up with new methods. So I think there is still more in the time series. We collect our time series. We think we extract respiration, heart rate, neural activity to some degree. I think there's more subtle information there. That's just there. That's why I'm pushing, like, Josh so hard to use edges to pull it out, because I think it's there. It's like, yeah, it's like Captain Ahab, like, it's there. We're gonna get the information. So I think we already talked about this. That's another possible future. And then I think I didn't talk about layers, and I think that layers is still in this sort of honeymoon stage of like, people are discovering it, and it's kind of looking hopeful. And everyone can imagine how it could be amazing if you collected the whole brain and had all this input-output information at a cortical level. You could really inform models as to what's going on, and it would open up an entire new dimension of functional MRI, and actually getting that information of how one part speaks to another part and how it receives feedback. But that's a big if, and the signal's noisy and it's messy and it's really hard and it's kind of slow. So, and there's a lot of open questions as to how to properly interpret it. But so far, I'm hopeful. So far, there's no reason to not be hopeful. I think that there's enough papers out that are kind of going in the right direction to be very suggestive. So I think that's a possible high impact thing in the future. And this is a little bit redundant, I know, but I sort of differentiate impact from just general trends. This is sort of like saying, okay, now what are the trends? High field, high resolution. Everyone's kind of talking about that at meetings. Multi-echo is kind of getting a renaissance, which is a good thing. Everyone should be doing multi-echo, and now everyone's kind of realizing it. Dense sampling, that's sort of picking up steam. Individual differences, I already talked about that. Dynamic resting state, everyone's aware of that. I think there's a lot of work to be done. Not enough groups are really working on advanced processing methods for that. Paradigm development, naturalistic paradigms, that's a big trend. Increased precision of the types of paradigms that's tailored to the processing method. That's a direction. All these things actually all of you know because we talk about this all the time. But multimodal, we have a multimodal group. I mean, it's no surprise that kind of what I care about is what I think is important. And that's what I talk about as a future trend. Multimodal and behavioral physiologic integration into the results. I think we use multimodal data, but I don't think we've sort of mastered actually integrating it in a more seamless way. I think there's a lot of room, a lot of science, a lot of engineering to be done with that. Big data. You go to OHBM, more than half the people at OHBM, I think, have never collected a data set. And so they're all using shared pooled data. And I think that's overall a good thing. I think there's a benefit to actually collect your own data in some contexts, but a lot of really well curated data and excellent code that's being shared as well. So these are the sort of applications that are sort of hot right now in terms of fMRI. Nothing actually that new other than brain-body interactions are becoming a bigger thing. And I honestly don't know exactly what this means, other than that the brain can affect things like our immune system, and the body can affect our cognition. So, and that's understanding the brain as not sort of like this isolated system, but this integrated system is something that I think more people are pursuing with other measures in the body. All right. Like I said, a strong trend. I think actually this is wrong. I mean, I don't think it's a strong trend. I think it's my own. I would like it to be a strong trend. I really do want to understand what resting activity is. I mean, I want to understand its purpose, what it means. Right now, it's great. It's one of those things that just kind of works, and it shows a lot of interesting information. But really, if we really are honest, we really don't know why there's resting state fluctuations. And so it's like so that just means that there's more to be had. And I'll talk a little bit about modeling now. And there's different types of modeling of data. There's a lot of good recent books written on modeling. And what people usually mean by modeling is that you can model the brain as like a series of networks that interact. You can model the hemodynamic response. But I think that what a lot of people would like to do is use fMRI data to constrain dynamic models and even mechanistic, like dynamic models that describe principles by how information is propagated in the brain, and also dynamic models that describe more mechanisms of how information is processed. Because right now we don't have any clue how a calculation is done in the brain. We have fMRI that measures a hotspot, we know it happens there, and then it might, feed into someplace else. But we don't even, we don't really know. We could imagine, we don't even know what a calculation looks like, of any sort. And so, when we say, oh, well, the brain has a model of the world and it's compared with sensory inputs, and then if it's different, it'll update that model. We have no idea what's going on. And those are just words that sort of fill in these big gaps of knowledge, like calling, it's like describing ether in the space or something like that. It's just, we have no idea. And so the question of modeling is so hard because, I've showed this before. The brain is organized across many different temporal and spatial scales. And, fMRI can get only what's in the red boxes. So you have, all the way from circuits up to the brain, you have the neurons down to the molecules, which we can't really see. And you have timescales down to neural spiking, which we can't see. But we can see pretty much, I think one thing that's awesome about fMRI is that you can see almost everything that happens in the temporal scale that we need to respond to. Most stuff in the world happens between 100 milliseconds and 100 years. So, and that's the time scale we can look at. And so this is sort of very tuned into how we respond to the world. Spatially, though, the question is, if you're building a model of the brain, and you want to figure out what aspects of the model to leave out, would you, in other words, you're trying to say, okay, what model can I build something that performs as the brain does, but I don't have to include all this stuff, this at different scales. What scale would you leave out? Maybe you could build a brain with something other than synapses or individual molecules or neurons. Maybe, but it's not clear. What is the essential scale? I asked this one question to neuroscientists, and it's like, what is the most important scale, physical scale, of actually understanding how the brain is organized? At least with fMRI, we talk about these large scale networks. And that's really just a conglomeration of millions of smaller scale networks. And it goes all the way down. And they're all feedback networks. And so how do we model the brain to actually understand the brain? So these are the questions that sort of leave me thinking, oh, fMRI will give you something, and maybe you can infer things and constrain things with fMRI, but you'll need a lot of help from other modalities. And I thought actually it was a great, just as I was starting to think about preparing this talk, Nicole Rust gave her talk last week, which I thought was really awesome and kind of eye-opening, and maybe it's what other people have said before, but if you look at the brain, the brain is essentially, I don't think you're going too far to limb to say that the brain is pretty much a complex dynamic system with massive feedback and many nonlinearities, on many different temporal and spatial scales that also has sort of emerged through the backdrop of evolution. So, how do you understand that? So the goal of modeling is to infer mechanisms. So what people try to do is, take data that's at one scale and create models that can predict that data. The problem is, it's a classic inverse problem. You can create many models that could predict this data. So, and not only that, it's an inverse problem. It's an inverse problem, but it's also an incredibly complex system with lots of feedback loops. And so, a lot of models, like for instance, you hear Michael Breakspear, who has amazing models, but at the same time, he's like, oh, well, I'm using this wave model to describe brain function, and keyword describe. It's not trying to predict. It's not trying to understand at a deeper level. It's just trying to describe it better. And so if that's our goal, just to better describe the data, then that's fine. But if you really want to understand the brain, I think you need to simulate it from the bottom up. Eventually we will. So this is a beautiful example of a logistic map. Basically, she was illustrating this problem with classic dynamical systems that have feedback. And this is a classic butterfly effect. And it's too bad I don't have this animation, but basically she showed like very simple equation, some relationship that goes between 0 and 1 and relies on the next step to feedback that changes the initial conditions from which it calculates. And it will be predictable, but if you vary just one parameter a little bit, it will look predictable, for whatever, 40 seconds or so, and then it will be completely different. And that's one aspect of being difficult to predict how the brain functions, because there's probably a lot of tuned nonlinear systems that are interacting, and we need to get a sense of how that's done. So, and also I like to think about in terms of this way. It's like if you're trying to understand the brain, it's a very different question. So I usually say, fMRI could be used clinically, basically looking at the brain as a black box that gives information that we can help people, but also to understand the brain. And right now, most of what I think we're doing is sort of some form of cartography. We're just sort of saying, okay, this part is important because it shows activation. That's useful, but it's not actually understanding. So, what Nicole started making me think about is like, do we really understand the weather? I think that most people could say, yes, we do understand the weather. We understand the weather. I mean, it's, can we model the weather? Pretty well, we can model the weather. Can we predict the weather? Well, that's a different problem. We can't predict it more than 7 or 10 days because, the weather is chaotic, it's nonlinear, it's sensitive to initial conditions. There's inaccuracy of data, limits of measurement, computational limits, grid resolution, atmospheric complexity, local weather, local feedback loops that all could change all the dynamics. And this is very analogous to the brain, I would say. You can generally understand, the statistical properties of the weather. You can do that with high accuracy, but do we really understand the weather well enough to say, oh, this is how it's going to propagate, and if we tweak this one variable, this is how we'll change the weather. There's no way we can do that. And the same thing with the brain. People are hoping that neuromodulation will help, but it's really like trying to tweak one aspect of the weather and changing the weather. It's like we don't know how that's increasing or decreasing activity of one node will actually change the dynamic system. So that might be open for many surprises as well. All right. So with the last couple of slides, I'm just gonna, I think that, so now how will AI come in eventually? So I actually like to think of this as sort of an anti-modeling approach, a very practical approach where you have AI, and let's say it's much better. It will get better. The algorithms will get better at doing more one-shot learning. And we can imagine training up an AI on massive amounts of well-curated time series data. And, it will discover ways of looking at the patterns that we've never even thought of, I think. And it will find associations with behavior and and also maybe with population type or phenotype of that we haven't even considered that we wouldn't be able to see. So I think that's sort of like the hope of how things might go in the future with AI, that it'll just go through all the data and find associations that we weren't clever enough to find. And like it's doing with protein folding, right now AI is being applied to, you take basic building blocks of molecules of proteins and it's coming up with folding patterns that we have not even thought about that shows is possible. So there's things like that that I think it can do analogously with fMRI. So every spatial and temporal pattern. So really what we're doing with fMRI is trying to understand all the spatial temporal patterns that exist and how and whether they're important or not. That's all we're really trying to do. That's all. If you summarize fMRI all down to one sentence, that's what we're doing. And AI is kind of optimized for that. It's and I think that once we ramp it up well enough and plug it into the data, it will surprise us with the spatial temporal patterns that it finds that we haven't considered. And also, likewise, it might even be able to, we might even be able to give it block equations, and it will come up with pulse sequences that we haven't considered. There's enough parameter space in pulse sequences that you can imagine combinations with AI that could be programmed on the scanner, or it can program on the scanner and just run it. That would be cool too. So I think those are two possible directions of AI. And another possible future direction, I'm just imagining this is like the ultimate final experiment that everyone would end up doing, is some sort of unsupervised learning where you have subject in the scanner and you have some sort of AI sort of controlling the stimuli and analyzing the data in real time and just iterating and monitoring everything, physiology. Maybe you could have simultaneous EEG with fMRI, and then learning all the associations. It could, just like whatever, just like Deep Mind sort of learned how to play chess in like an afternoon and became a grandmaster. You can imagine AI. Obviously you're limited by human physiology because a person has to be a subject, but you can imagine them learning a lot about fMRI mapping to behavior and stimuli through this sort of experiment with a highly motivated volunteer. So that's another possible direction of how AI could potentially go. So what could rapidly change everything? So I may have shown this in other contexts, but one powerful clinical application would really catalyze fMRI, because then the big vendors would pay attention, because there's a market there, and they would start to devote a lot of man hours to getting fMRI working really well. That would change everything. Something that's robust, that doesn't rely on hemodynamics would change a lot. I think that the impact would be less than what we think, because fMRI is pretty good. And I almost say that there's an advantage to integrating a little bit over time with the hemodynamic response. Room temperature superconductors, we're pretty close to that. There's kind of a science to it, but any progress is kind of random. It's sort of serendipitous. So, but eventually when we find it, we could have wearable MR scanners. We wouldn't have to have a Dewar cooling down the superconductors. So that's another possibility. It would be kind of dangerous though. But anyway, that's let people figure that out. And also, if the hope for potential of layer fMRI that I talked about is realized, whether it can actually truly look at hierarchy and feed forward feedback mapping, that would change kind of how we design our experiment. Like half the field would design their experiments differently. All right. I'm actually not going to go over this. There's a really good paper that was recently written. It's pretty good. It was a good perspective on, written by Chaogan Yan, some of his friends, on insights from leading experts. I just happened to be reading this when I was preparing my talk. Basically, it's various people saying similar things that I have reiterated. Big data, the need for mechanistic models that explain as opposed to describe the data. There's a big difference there. Christian Beckman, I think that there's basically talking for large data sets. Daniel Margulis, who discovered gradients, talking about, he's kind of curious why it's, whether we can answer the question why certain specific species have cognitive abilities and others don't. Michael Fox is all for neuromodulation based on fMRI guidance. Paul Thompson basically is looking at, trying to associate genetics with fMRI and structural mapping. And he also is a big proponent of AI for greatly enhancing our ability to extract information from the data associations. Russ Podrak talks a little bit about the research domain criteria, and he's really trying hard to understand how we can use imaging to elucidate diagnosis, basically. What are the features? And Thomas Yeo has sort of caught on to the idea of doing personalized individual subject mapping. And then finally, Vince Calhoun is all for multimodal integration. He's probably leading the world in actually doing it, his group. So with that, I'd just like to leave a quote of a famous quote by Roy Amara. So we tend to overestimate the effect of technology in the short run and underestimate the effect in the long run. So all these things that might happen probably won't happen for another, longer period than I suspect. But I do think that this general trend of AI integration and trying to use multimodal imaging to understand the brain is going to actually build over in the long run. But so that's my best perspective on I think what the future is. So we're all hopefully positioned in the right place to be able to work on all that stuff. So thanks. All right.